This is the first lecture in Unit 2 of Nanotechnology, and we are going to do a little bit of bonding review and intro nanomaterials. So first in class, I had everyone brainstorm what are the three main types of bonding again, and those people who took chemistry more recently can more easily remember that there's ionic bonding, covalent bonding, and metallic bonding, and all three types of bonding exist in nanomaterials. So what do you remember about each of them? Well, for ionic bonding, ionic things are often salts, and there is a transfer of electrons, meaning one atom actually gives its electron or multiple electrons to the other atom. These form between a metal and a nonmetal. The metals give up their electrons to the nonmetals, and now the metals have a positive charge and the nonmetals have a negative charge, and of course you guys know that positive and negative charges attract, and that's what holds the atoms together. That's called an ionic bond. So here's an example where sodium gives up an electron to fluorine, and now sodium will have a +1 charge, fluorine will have a -1 charge, and the two will be ionically bonded together. There's also some terms, anion and cation. Cations are for positively charged atoms, anions are for negatively charged atoms. Next is covalent bonding. This is where the atoms actually share electrons. So here is an example showing that two hydrogen atoms, which each have one electron, they share and they form the H2 molecule. Those are called the bonding electrons between the two hydrogens. Then we've got two fluorines together. Same thing, they're the bonding electrons between them, and the lone pair electrons are the other ones that aren't between the two atoms. Covalent bonds usually form between two nonmetals or more. Finally, there's metallic bonding, and this is when there's a sea of valence electrons, and that's what makes metals such good electrical, thermal, and thermal conductors, and also things that have metallic bonding are ductile, meaning they can be pounded into a very thin piece of metal, or they can be drawn into a wire. Then we did a scavenger hunt in class to kind of look around the room and actually apply this knowledge. So I had some salt sitting around the room. That was a great example of something that had ionic bonding. A lot of people brought water up to the front for their example of covalent bonding and found something metal in the room to bring up. I also talked a little bit about how intermolecular forces, the forces between molecules, are so important at the nanoscale because, again, gravity has less of an effect, so these forces really dominate. And I just briefly mentioned these different types of van der Waals forces. Then we got into nanostructures. So there's different types. There's particles, which you can imagine like a shrunken marble or a shrunken down cube. There's wires or nanotubes. There's nanofilms, which is really a thin layer or thin coating. And then there's also these porous materials, kind of like mini sponges. So first, particles. Particles are mostly surface atoms. Bulk solids have typically less than 1% surface atoms, while small nanoparticles can have around 90% surface atoms. Van der Waals forces dominate between the particles. There's not that many bonds between the particles. It's mostly interparticle interactions. They're more reactive, so they're useful as catalysts, meaning they speed up reactions. And here's some scanning electron microscope images of some different nanoparticles, some different shapes, and some nanocubes. Okay, then there's nanowires, nanotubes. Here's an SEM image of some of them, and this is clip art showing some carbon nanotubes. So they can be hollow in the middle, or they can be solid all the way through. There's a lot of uses for carbon nanotubes and different nanowires in electronics, optics, and anything where they're trying to make stuff stronger, strength-based applications. For films, there's a lot of surface area, obviously, in this sort of a nanomaterial, and what's cool is that you can often have these nanofilms self-assemble. So, for example, you've got some sort of a metal and something like sulfur which bonds to the metal, and to that sulfur you can attach anything that you want, and then voila, you've got a thin film. Finally, the porous materials. There's a few terms here. You can be talking about micro, meso, or macroporous materials depending on the actual pore size. They make great water filters. That's what that picture is showing. They can trap bacteria, other contaminants in the water, but let the actual water molecules go through. Other applications, they make great insoles for shoes or thermal insulators, which is really helpful for like hiking boots or ski boots in blizzard conditions. And they also have a lot of medical applications like bone tissue engineering. They can be used for drug delivery. It's a fairly new thing that mesoporous structures are getting so hot. Okay, then there's a more crystalline type of mesoporous structure, and it's called a zeolite. These have been around for a while. There are lots of naturally occurring zeolites, and again, these are basically like sponges, only really small. Their pores can be sometimes as small as 0.3 nanometers, and they can hold a very small amount of liquid, for example. So again, they're useful as catalysts to speed up reactions. Another really cool use is they can be used as adsorbents to get rid of contaminants, like getting rid of heavy metals in nuclear waste. So there's lots of different structures within this area of zeolites. And then we did a little scavenger hunt in class again, where people had to find an example of something where if you shrunk it down, you would classify it as a particle, a nanowire, a thin film, or a zeolite. And that is it for that.